Hawaii startup built a 3D printed Navy boat. Building a military boat traditionally requires molds, fiberglass layup, skilled labor, a fixed factory, and weeks of production time. A Hawaii-based startup called Voltage Vessels is working to replace that entire process with a 3D printer, a spool of basalt-reinforced thermoplastic, and a digital file that can be sent anywhere in the Indo-Pacific and printed on demand. The company, founded and led by Sam Young, is built around a material it developed called Eclipse X9, a composite that combines recycled PET plastic with chopped basalt fiber, the same volcanic mineral found throughout the Hawaiian Islands, into a printable structural material engineered specifically for marine and defense applications. Voltage Vessels has submitted a 6-meter rigid hull inflatable boat for U.S. maritime defense evaluation, with the program assessed for potential integration into autonomous naval programs. To understand why this matters, some background on how military boats are currently built is necessary. A rigid hull inflatable boat, or RHIB, is the type of fast, hard-bottomed inflatable craft used by Navy SEALs, Coast Guard boarding teams, and surface warfare units. For everything from personnel transfer to maritime interdiction, they are typically manufactured using fiberglass or aluminum hulls built in fixed facilities with specialized tooling and shipped to wherever they are needed. That supply chain works well enough in peacetime, but it creates serious logistical vulnerabilities in a contested maritime environment where forward-deployed forces may need to replace damaged platforms quickly, far from the nearest shipyard. Voltage Vessels is proposing a different model, one where the manufacturing capability travels with the force rather than sitting in a factory on the continental United States. The company calls this its distributed composite manufacturing model, with Hawaii serving as the pilot node of a framework designed to scale across the Indo-Pacific. The concept is straightforward: establish a network of regional production facilities, each capable of printing hulls, flotation collars, and structural components from the same digital design file, using locally produced Eclipse X9 material without requiring the molds, tooling, or supply chains that conventional boat manufacturing depends on. The Eclipse X9 material that makes this possible is not simply a commercial plastic filled with mineral fiber. The University of Maine's Advanced Structures and Composites Center, one of the leading large-format additive manufacturing research facilities in the United States, validated the material's mechanical performance under Project ID UMTC 231008. Testing showed tensile strength of approximately 108 megapascals along the print direction and 365 megapascals perpendicular to the layers, compared to 492 and 97 megapascals respectively for HD Pro, the established benchmark composite material for printed marine vessels. Bending strength tests measured Eclipse X9 at 11298 megapascals in the primary direction against 6040 megapascals for wood-filled PET, a common alternative. The material has also undergone more than 24 months of saltwater immersion, benchmarking with greater than 90% strength retention over time, and water absorption stays below 0.4%, a critical figure for any material used in marine hulls where water uptake degrades structural performance over years of service. Basalt fiber as a reinforcement material has a longer industrial history than its current defense technology positioning might suggest. The Soviet military used basalt fiber composites in armor and infrastructure applications during the Cold War, drawn to the material's combination of chemical inertness, non-conductivity, and resistance to corrosive environments. Modern industrial applications include rebar for concrete in marine environments, fire-resistant composite panels, and impact-resistant structural systems. What Voltage Vessels has done is reformulate basalt fiber reinforcement specifically for large-format additive manufacturing, developing a compounding process that produces consistent pellet and filament formats suitable for both industrial-scale CA-class printers and smaller desktop systems. The electromagnetic properties of Eclipse X9 carry specific relevance for military applications that aluminum and carbon fiber composites cannot match. Basalt fiber is electrically non-conductive and has a low dielectric constant, meaning it does not reflect radar energy the way metallic structures do, and does not interfere with the radio frequency signals that autonomous naval systems depend on for navigation, communication, and sensor operation. The company's documentation describes the material as RF transparent, though this characteristic remains under evaluation for specific frequency ranges for unmanned surface vessels that carry radar communications antennas and electronic warfare equipment. Building the hull from a material that does not absorb, reflect, or interfere with those signals is a meaningful engineering advantage over conventional hull materials. The 6-meter RHIB was printed using Seed's large-format additive manufacturing system, a Dutch industrial printer used by multiple defense contractors for whole-scale composite production. The hull was printed in HD Pro Composite and submitted for U.S. maritime defense evaluation for potential integration into autonomous naval programs. The manufacturing model voltage vessels is building around Eclipse X9 addresses a problem that has become more urgent as the Pentagon invests heavily in distributed maritime operations concepts that depend on forward presence in the Pacific. Shipping replacement hulls from the continental United States to Guam, the Philippines, or Japan takes weeks and requires cargo aircraft or sea lift that may not be available in a contested environment. Printing a replacement hull locally from a digital file using material produced regionally takes days and requires only a printer power and feedstock. The company's production capacity is described as scalable to 15,000 metric tons of material annually from U.S.-based compounding infrastructure, equivalent to 15 million 1-kilogram filament rolls per year, with regional licensed compounding partnerships planned to establish distributed production nodes across the Indo-Pacific framework. The circular manufacturing dimension of the Eclipse X9 platform is unusual for a defense material and carries significant long-term sustainment implications because PG thermoplastic can be remelted and re-extruded without significant property degradation. Printed components can theoretically be shredded, repelletized, and reprinted into new structures at the end of their service life for forward-deployed naval forces operating in locations where waste disposal and resupply logistics are both challenging. A material that closes the loop between production and end-of-life handling has genuine operational value beyond its structural performance.